Hi, Priya. Good evening.
Yeah, hi Daniel, how are you?
Good, and you?
Yeah,
Hello.
we slept and just got up. Uh, Daniel, a quick question about next week. Do you also want to take a session next week, or
Yes, you said you'll not be available, right?
no? No. So we just realized that we have a flight in the time of actually the night class is 3 to 5 in the night for us, and now this one is 12 to 2. So we can probably be the first half on 24th. That is for the more for the morning session. There's no problem. We can do that. But for the evening session, we can take the first hour. So will you take 1 hour and we take 1 hour next week?
Okay. Yeah, so no problem. So you probably just take the first half
Yeah,
next week.
yeah. So we can take the first half and then we go to the airport because we
Okay.
haven't. Okay, we'll write on email on WhatsApp.
Yeah, sure. Okay, cool.
So now we'll go on like we did with the previous session, right?
Yes.
Okay. Okay, fine. Okay.
Hi, everyone. Good evening from here, and good morning, good afternoon, wherever you are. We are back again. We met earlier in the morning, and then this week we are talking about machine learning. So we'll just wait just 2 minutes before the start time. Okay, it's almost time. Okay, I think we'll start now. Lebo, are you there? Hi, Lebo, are you there?
Daniel, what is that?
Yeah, just to start the recording, that's why.
Oh, yes, yes. Yeah, I already started the recording. Yeah.
Oh, okay. It's not showing, I'm not seeing it on my screen. All right then. Cool. Is there any showing thing apart from this showing on my screen? I know this sliding. Okay, good evening, everybody. This is the week 6 of the BRICS Idea Data Analytics program. We understand it's been a very long journey for some of you who maybe for the first time is participating in this kind of program where you're forced to learn a couple of new things in a short period of time. And yes, it can be tough, but we believe that you're progressing. So congratulations for coming along this far. This is the week 6, and then after this week, next week we'll wrap up the lecture series, and then in the week 8 we will discuss just the performance and then outcome feedbacks and all that for people who participated in the program submission. capstone project submission. All right, so since 6 weeks ago or 7 weeks ago, you have been learning about data, you have been learning about programming, you have been learning about analytics. And one thing that is conversant in all of these conversations is that there is a lot of data and you need to understand how to analyze this data to generate results. And before I proceed to talk about machine learning, a few little background or historical background. Maybe I'll say they put it this way, that for a number of years, we have seen development in computer science, in computing, maybe mobile devices, desktop devices, laptops, and the rest of them. And today, computing device has become a household device. It's no longer something that is only applicable for those in businesses or corporations. Today, almost everyone has a computing device in their hands in the form of a smartphone or even a computer or a tablet. Now, what it means is that you have a device whose job is to process information. And this information can be of many shapes, can be of different forms and sizes. And just giving you that clue. And then this information can vary. For example, if you are a scientist, what it means is that while you do your research, you collect data, and the data is passed through a computer because you need to do some analytics, you need to do visualization, you need to do some modeling, you need to do maybe some sort of maybe machine learning, deep learning, and the rest of them. On the other hand, you also have people who may be in the entertainment industry, in the business world, and the rest of them. So data is being collected on a daily basis. And this data can be useful. So as data developed over time, people started thinking about how can we make use of this data, because you are processing this data over time and you are not able to catch up with everything that is happening. So maybe how can we mine the previous data, or how can we use the data that we already have to predict outcomes, future outcomes? And that is where the idea of machine learning comes in. And machine learning is a field of artificial intelligence whose job is to help you learn from data, where you give computer or processing systems the ability to learn from data, the same way you have been learning from data over the last 6 weeks, where you have been playing around with coding, playing around with data, trying to perform some analytics yourself. So that's what machine learning is all about. It's far bigger than this. It's a very big field. Today, it's one field that has almost engulfed every other field, or it's related to every other field. Almost every field today has something to do with machine learning or artificial intelligence. And then, yeah, so just like I said earlier, the historical perspective, which is that we don't have tons of data. As an astronomer or you're a scientist, today you have tons of data coming from different sources, instruments, observations. Those in atmospheric science have instruments for collecting atmospheric data. Same thing, oceanographers, astronomers have telescopes that are used in collecting data, both space and ground space-based telescopes. So you use all of these things to collect data. On the other hand, businesses that you see out there, they also collect data of different shape and sizes. Businesses, e-commerce websites, you see them, they collect data, they show you those data, they market those data to you, and the rest of them. So banking system, telecommunications. Now, there's enough data. Now, the next question is, what can we find in this data? How can we manipulate or analyze this data optimally without, breaking the bank and whatnot? And this is where developments have been in machine learning, looking at different methods to analyze this data. So just moving forward, so I've already described what machine learning is, the study that the field that allows computers to be able to learn from data without being explicitly programmed. So what it means is you have a set of algorithm, and and then with that algorithm, you pass your data to it, and then you allow it to process the data over time. And as it's processing the data, it should be able to learn a pattern, find pattern in the data. It's just like you yourself, supposedly you come into a space over time, you get used to it, begin to understand directions, where things are, what and what not, what should be and what should not be. So the same way, we've also been able to artificially allow computers to do this thing. And a good example is supposedly you have images of cats, and then you assemble these images and pass it to a computer, a machine learning algorithm. What it's going to do over time is that it's going to start looking at each patch of this image, pixel by pixels, to begin to understand the composition of the image, and should be able to tell, oh, maybe this is a cat, or even not necessarily say, it can start by understanding the features. Maybe this is the tail, this is the ear, the eyes, the nose, the feet, and whatnot. And over time, it also learns to be able to understand the shape and even disentangle a cat from a fox, from a rat to a dog to whatnot out there. So this is the process. Just some way we are meant as humans to read, learn, practice, and over time you understand the topic, just like the same way you're taking this course. After the lecture, you go back to the learning resources and then you go through it over and over again. You consult other materials and then with time begin to understand the topic. So what it means is that we need to expose this data to the machine learning to the computer in a way that they can be able to process the data over time, and over time they're able to learn this. So it actually has a process. The process in the sense, just like as humans, yourself, you have to take your time to study and read before you understand any topic. So machine learning, we do also have our own procedures. So it has its own procedure where you have to prepare the data in a certain shape or form. And then when you prepare that data in a certain shape or form, this is usually called a training data set. When you prepare it, you pass it to your predictor. So in machine learning, we do have different kinds of machine learning algorithms that we can create. We call them predictors. And then we train these, we call them estimators, sorry. And then when we define these estimators, we pass in the training data set. And after it trains for a period of time, you now take that model and use it to make predictions. And then after making the prediction, you go through the process of analyzing the predictions, or more like evaluating the predictions to see if the model is picking up or understanding the task of maybe doing a classification problem or regression problem. So if it's not doing quite well, then you should be able to say, oh, this model is not performing very well. The same way a teacher will, after teaching students, will organize a test and say, oh, come write a test or quiz, and then evaluate their performance. From the performance of the student performance, you can say, oh, this student is doing quite well, or something is not right, they are not passing the exam, maybe something needs to be done. So it's the same process, So we're basically just taking our own learning, more like our own learning process, and then giving it to a computer to also follow the same process to learn. But the only advantage of computer is that it is very fast, so it has a lot of processing speed. It doesn't take a lot of time like humans to learn or understand. It's able to learn very fast. It's also able to not learn. Okay, yeah. So that's it. Let's talk about types of machine learning. Machine learning are of different types. We have the supervised learning, we have the unsupervised learning, we have the reinforcement learning. And maybe I didn't basically talk about the other aspect of artificial intelligence. We have machine learning, we have deep learning, which can be of different forms, things like object detection, computer vision, and many other segmentation, and many other things you can think of. So for supervised learning, it happens to be one of the easiest part of machine learning, or more like one of the common aspects of artificial intelligence per se, because it tends to deal with tabular data a lot, or more necessarily tabular data, but for majority of the time, it tends to deal with tabular structured data. That's the word I'm looking for. It tends to deal with structured data. you know, if you have taken a course on some data, maybe things like big data, you will learn words like data can be of different form. You have structured data, you have semi-structured data, and you have unstructured data. So majority of the time, supervised learning and even unsupervised learning tend to deal with structured data. Now, the structured data, example of a structured data is some of the data sets you have been using from week 2 to week 5, where you have a tabular data set that you can read with number, you can also read with pandas. So it's more like data represented in an array that can be represented as an array or as a data frame. Yeah, but you know, these things can increase over time. Maybe when you're not dealing with matrices, where you now have complex dimensions or more than 3 or 4 dimensional data sets. So for supervised learning, you tend to have 2 sets of tasks to do in supervised learning: classification and regression. And another unique thing about supervised learning is that you tend to have, when you have your data set, you tend to prepare it in 2 forms. What it means is that you need to understand the data set, prepare the features. The features means the properties. A good example is, say you want to evaluate, or you want to check the performance of students in your country, maybe grade 1 students or grade 6 students in your country. And what do you need to do? You need to get their information about their demographics, their health condition, maybe their age, their other things, health, and many other things you can think of. Maybe family background, or maybe number of siblings, maybe whether their parents are there or not, all that. So why are you doing all of these things? You just need to get more information, because these informations can help contribute to understand how there are properties that you think can help influence the outcome of the student in terms of how the student performs in a class. So I'm trying to use these examples to relate to what you can do with machine learning. So at the same vein, if supposedly you have you want to train a data set, or maybe a classification, maybe where you want to train a model that predicts maybe stars or galaxy. What it simply means is that you need to get data for stars, and this data for each star you record their different properties. It could be their distance, it could be their size, it could be their magnitude, it could be maybe other things that you think could be relevant and all that. So, and then that is you confirm the kind of object this is, and then you leave it with the properties, and then at the same time you do it for the many other classes. And then boom, you have something that you can say it's a well-prepared data set that can come as input and output. So the features is given as input, the labels is given as out, it's also provided as outputs. So what it means is that you are giving it this chunk of data and say, hey, I want you to look at this data. As you're looking at this data, this feature correlates with this label. This feature correlates with this label. Now, labels could be, or outputs could be of different types. It could be discrete. It can be a discrete variable. It could be a continuous variable. Discrete could be something that is like countable, like 1, 2, 3, 4, 5, or 10, or 15. On the other hand, regression is things that you know are not easily that cannot be that are not distinct. So it could be more like real valued numbers. Like, for example, a good example here is let's say the weather condition. Weather condition can be transcribed or described in 2 forms. Say, for example, somebody says, okay, what's the weather condition now? Especially for temperature, you can say, oh, it's hot or cold. When you describe it that way, you are dealing with classification. On the other hand, when it is more like, excuse me, what's the temperature now? And somebody says, oh, it's like 13.8 degrees Celsius. In that case, it's no longer a condition of whether it is hot or cold. The person wants specific value. So in that case, you are not dealing with a continuous variable, because in this case, you can ask these questions multiple times, and the value short for every 1 hour or every 30 minutes, the value will continue to change, maybe in decimal shape. So these are more like the basics for I'm thinking of trying to like trivialize it for you to understand. So so here is how supervised machine learning is. So you tend to always have input and then labels. So on the other hand, you have a regression, and then like I said, regression is a case where you now have continuous variables where you could be like, what is the body mass index of a human being or that of an animal? What is the age of people in your class? What could be the weight of a device or anything you can think of? Yeah, so this is how it can be for supervised learning. On the other hand, for unsupervised learning, we tend to, it's a case where you only have input, but there is no output. So you know the features, but you don't know the distinct property to say, okay, oh, I think this is the exact value for this. So you don't have those data, and what you just need to do is pass it to the model, and they say, model, I'm sorry, I have the properties of this data set, but I do not have their exact outcome or output. So can you help me look at this data and see if you can find a pattern? Like I said, machine learning is all about pattern finding. The same way, even in science, a lot of it is involve finding pattern a majority of the time. Sometimes it involves you doing advanced analytics or even doing modeling. Now, looking at this, looking at this graphics here, you can see that clustering, it's a way of maybe, just like the name suggests, you are given series of data, and your job is to look at them one after the other and see the relationships in them, and then see the group the ones that have similar properties together. So I believe this is something that you can do. Supposedly you are given a piece of toys or of toys, maybe of different toys. You can pack of toys, and then you can just look at the distinct ones and then put them together. You understand? Good. Group them together. Yeah. So on the other hand, machine learning can do this effectively. We have tons of a couple of clustering models, algorithms for doing this in machine learning. So that's by the way. So as you can see here, the clustering, the colors tells you these things are clustered together. It tells you, oh, this does not fit into this tree, so it is alone. This happens a number of the time, even when you're not doing machine learning. Sometimes even when you do distributions or do scatter plots, you can see some objects that tends to stand out, and we oftentimes refer to them as outliers. Yeah, so as described earlier, you have a supervised learning where you have the data and the labels. So supposedly this is a data set, this is your training data set. You look at this, you say, oh, this is Georgian. Oh, this is Tibetan. Let's say you have a classification model where a classification task where you're looking at characters. What do you guys call it again? Alphanumeric characters. ASCII, no, yeah, these are all ASCII characters anyway, but you're just trying to look at it for different languages. Yeah, so looking at this, oh, this is Georgian, hey, this is Tibetan, oh, the other one is Indian, the other one is Mandarin and the rest of them. So as you pass this over time to machine learning model, is able to now understand that, oh, this is Georgian, oh, this is Tibetan and the rest of them. So this basically what the training phase looks like. And then if the test set is also where you now have some test set is a case where you also have the same information like the feature, in the feature, the input and output, but you reserve it because you want to use it to test the model that you have trained with the training data set. So what you want to do is, supposedly you use your training data set here to train a model. And then when you're done training it, you use the model to predict these things. And then when you predict it, it's going to now tell you, oh, whether you're correct or not. For example, in this case, you can see that based looking at the guesses, the labels and the guesses, you can see that for 4 out of 5 of the guesses, it was correct. And then for one of it, it's wrong. So in this case, how do you evaluate the accuracy? So this is a case of classification. You do the usual arithmetic. So it did like 4/5 correct. So that's 80% accuracy. Yeah, but accuracy is not the only way of evaluating machine learning models. because sometimes, especially in case of class imbalanced data sets, it's not ideal. Yeah, because it's not able to, in that case, if it's not able, it's not heuristic enough, or no, it's not agnostic enough to understand the differences in that. So another type of machine learning that we have is reinforcement learning. Reinforcement learning is an extension of this other set of learning, in the sense that it's a case where you're allowing the computer to perform certain kind of task, and you reward them for you design a model such a way that the computer can perform certain tasks and then gets rewarded based on how good they are meeting their desired objective. So a good example here is supposedly, okay, a good example is, I'm not sure many of you've heard a lot about driving cars, self-driving cars, right? For self-driving cars, they tend to use reinforcement learning. So they more like explore their environment, based on conditions that have been defined earlier, how they are able to play safe in that environment. Yeah, that's a form of reinforcement learning, and this is becoming very useful in robotics, becoming very useful in mechatronics, even in this era of large language models. We are now seeing a lot of reinforcement learning helping, where you can see some, for example, ChatGPT, DeepSeek, Google Gemini, and the rest of them, Mixtral, Llama, Meta. They do have employ this in their trading algorithm. So we'll not be talking about reinforcement learning because it's not in the scope of this, but we just wanted to mention it for those who are interested. There are quite a few resources you can find online for learning about reinforcement learning. I think there's an open, I'm not sure if it's Harvard or MIT class, lecture on YouTube that you can find that talks about reinforcement learning. You can also find it on Hugging Face. They do have a course offering reinforcement learning. You can also find it in other places, maybe things like Udemy or Coursera. Yeah, so let's talk a bit about data and how they are represented. I'm not sure I should delve into this because you already understand data. We've been talking about data for the past 6 weeks. So you already know how the data is and how they are represented. But just for formality's sake, let's also look at this again. That when we talk about data, it is not different. Machine learning data, it is no different from the data that you're already used to, that you've been playing around with. But the only difference and the only thing that you need to pay attention is that you need to have the data in a sort of train and test set. So you need to have it. Nowadays, it's even 3 sets. We call it training, validation, and test set. But because we are not going fully into machine learning for this course, we just want to give you an overview, and then you can go play around and maybe take courses online, or maybe in subsequent sections we might organize a full training for machine learning. So you already know that data can be categorical. You know, data can be ordinal. You also know it can be numeric. Oftentimes these cases are quite good for classification. Numeric data set also might be very useful for what's it called again? For regression. But bear in mind that the features can also be categorical, features can also be ordinal, can also be numeric. Yeah. And then when you have this data, you split and then you pass it through your modeling. So let's look at this example here. You have the handwritten digits. This is a very one of the earliest data sets for machine learning and deep learning. If any of you have taken deep learning, any deep learning course, you probably you see that this is usually like the hello world for deep learning, especially if you take the ones from, I think, even TensorFlow, or the free ones offered by PyTorch. Yeah, so this is a handwritten digit. Some of you do have, probably definitely you'll find your handwriting style in this if you explore the data enough. So you can see that these things are quite images, and these images have been, 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 th are actually pixels, and they are actually arrays. So we're going to play the example in this in the next few minutes, and then yeah. So this data set, irrespective of the shape, can also be very useful for you to get started in terms of how you prepare your data set. But just a quick overview, especially for those who will be interested in doing things like computer vision or image analysis. You already know, I think Prayer did talk about it, if I'm correct, 2 weeks ago, when we were talking about astronomy image data sets, that these images are actually pixels. So when you're looking at image, you can zoom in until then you get to more like the lowest part of the image called a pixel. And the pixel is more like a data point, and it represents an attribute, unique attributes. Yeah, so, and say 400 attributes represent a 20 by 20 bitmap. Yeah. So we've talked about this enough, and this is also a case where you now have series of data sets, and then you now want to transform it. Well, this is a case of multi-class classification where you have different classes, cat, dog, horse, parrot, and you transform it into numerical values. And then supposedly you have the other features. You can transform them in certain numbers that it's easier to break them in a way that computers can, computers tend to like zeros and ones. And sure, that is what they do. Everything that you run on the computer that might look like image, it still finds a way to transform to zeros and ones in the computer. So no, so not instead of wasting a lot of time, we need to jump into some of the hands-on that we've made for this week. So I'm going to stop sharing my screen and find the notebook for this very lecture. If any of you are able shared I think he did share the notebook or resources for this week, and you can get started with it. Some of you may have maybe started already. So we're back to this notebook is also available in the GitHub repo. If you go to Week 6 folder, you're going to see all of these resources, including the PDFs, including the slide. If you are interested in the slide, it's actually there. It's actually here. If you click this notebook, you will see it. So this is a notebook from the Escape Summer School 2022, and then they do have a couple of PDFs there that I also shared with you that could be of useful to you to understand these concepts. Now let's jump into the notebook because of time. Let's look at the first one. The first one attempts to give you a background, notes on machine learning and how it is relevant for astronomy. Like I said earlier, machine learning is existing. It's there because of the tons of data that we have, and we are living in a computing era. So we want to easily use computers to analyze this data, find patterns in it that could be useful for business, could be useful for scientific discovery, especially for those of you who are scientists or want to be scientists. You should be thinking about discoveries, and discovery doesn't necessarily have to be for you to go and start reinventing the wheel. It could also be at looking at previous data that already exists. So you can become a machine learning specialist, and your job will be to look at data, maybe based on the background, work a bit on the data, perform some analytics, do some transformation, and then boom, pass it, train a machine model on it, and see if you can make some new discoveries or find some useful patterns that could be useful for future predictions or classifications. So we do have tons of telescopes currently that are doing great works. Many of them have been mentioned to you in the past. You've heard of Gaia. I'm very sure some of you have played with Gaia data sets. You also played with test data. You played with test data last week. And then you also looked at things like radio data I think 2 weeks ago or so, and also some infrared data that when we looked at oh, no, same last week, yes, when you were looking at some time series data. Yes. So now This is quite relevant. We have the Zwicky Transient Factor, ZTF, which is a ground-based telescope. That its job is to also find transients. But more recently, we've had the Vera Rubin Observatory, which is a state-of-the-art observatory that is kickstarting very soon. It has been in the development for years, for decades. I'll probably say close to 2 decades. And then now, it's going to get its first light. I think first light celebration is happening in South Africa on the 23rd, actually. For those, some of you are in South Africa may have seen the email. Yeah, so what it means is that you don't have instruments that can make new discoveries, that can make tons of observations at night, and this data will be analyzed. You understand? And it's not something that one individual can do. So you need communities, you need people who understand machine learning skills to take this data and make good use of it. So that is what this notebook is all about. There's no thing you need to run here. All you need to do is to read about it. It introduces the concept of machine learning, model training, and how to also what I've described in the slide, the supervised learning and unsupervised learning. Also provided a few examples in terms of astronomy. Yeah. So we're not going to waste a lot of time. And also provided some use cases. These are use cases that are relevant for you, especially for some of you who are starting, or some of you that want to play around to maybe around machine learning and thinking of what you can do. So here are some few examples. Like I said, Google is your friend. You can also go online and see what people are doing. So there's nothing to run here. This is just for you to read and understand. Then in the second notebook, this is where we try to do a demo, first demo for machine learning. And like I said, for modular machine learning in Python. Python is very useful, very good. It's actually one of the, I'll probably say the most common programming language for doing machine learning. And Python is it. And scikit-learn, like you said, you have been introduced to packages or models in Python. So you now understand that there are different packages for performing different tasks. If you want to do numerical analysis, NumPy is there for you. If you want to do data visualization, Matplotlib and Seaborn and Plotly is there for you. There are still other ones. If you want to do machine learning, then your best bet is to kickstart with scikit-learn. This is why this second book is called Introduction to Scikit-learn. Now, scikit-learn is like every other Python program, a package, but this is specifically designed for machine learning. So what it means is that any form of machine learning task algorithm have been already designed and written in scikit-learn, so they're available for you to run. There are quite also some types of models that are not available in scikit-learn, like you have the XGBoost. Some of you may have heard of XGBoost, the gradient boosting models. There's also LGBM, some light GBM, yeah, for those who want to do advanced classification. But we're talking about scikit-learn here. So scikit-learn allows you to do processing of data. It allows you to do classification of data, allows you to do regression, allows you to do clustering, and many other things, advanced analytics, or even robust and complex machine learning. Maybe in a case of where you're dealing with large data sets, or cases where you're dealing with data that is quite very complex, that is not, you're not able to find pattern easily. So it also comes with tools that you can use to tune and find pattern in these data sets. So we've provided a few examples. We're going to talk about here training and testing this data. So just to kickstart, you already played around with some data sets that you may have loaded from pandas or I think Seaborn in the past during your data visualization section. I think that's week 2 or week 3. This time around, we're going to load a toy data set. Some of you may have heard it, some of you may not have heard it, but just know that it's not something that is so complex, but this is just an example of data that you can start with, and you can probably will see how it differs. So we're going to play with this store data set and we're going to delve into real world data set. Now, in this example here, we are importing the pandas, scikit-learn dataset module. So scikit-learn can be installed with pip install scikit-learn. Oh, sorry, this is not provided here, but it's actually, if you click this, let's see, it should be able to take you here, and there should be a install. Yeah, if you come here to the install, it's going to should be able to show you how to install. Yeah, it's going to tell you how to install with pip. You click the pip. I think it should be, yeah, pip install scikit-learn. This is if you already have it before, you can upgrade. So it's usually the same pip install scikit-learn. But if you want to import it into your notebooks or into your Python code, you have to call it as sklearn. SK for short, maybe like short for scikit or science kit. So sklearn, we import data sets. Now we need to, there are a couple of models or algorithms, types of machine learning. We say there are classification, there are regression. Now in this classification and regression, you still have different types of algorithms for this task. So your job is always to test out which one that is. All of them are very useful, but they can perform very well depending on the kind of properties of your data. So that's why majority of the time machine learning is an experiment where you have to play around different types of algorithms to see which one performs better. If you come back here to this notebook or to this website link, you will click, if you click here, you can see it tells you supervised learning, and then start listing for you different types of model and supervised learning. Support vector machines, stochastic gradient descent, nearest neighbor, which is the one we're going to play with, Gaussian processing, naive Bayes, decision trees, and ensemble. So there are quite a number of them here. So let's go back to our notebook, and here you now have this. So we try to import the nearest neighbor one called k nearest neighbor classifier, because we want to do a bit of classifier task here. We also import support vector machine. You already seen it in the list there. And then from metrics, from the scikit-learn metrics, we import accuracy score, precision score, recall score, F1 score, and confusion metrics. So if you remember in the slide I showed you earlier, we talked about that after training your machine learning model, you need to evaluate it. So these are the common functions that you need to evaluate your classification model. And then here is an easy to use function to split your data set. Remember we said you can have a data. Data is no different from different kinds of data that you already have. If you think that this data can be useful for machine learning, don't worry. All you just need to do is to take the train test plate. It is going to help you split the data into two folds, one for training and one for testing. And it can partition it based on the percentage of test that you want. Yeah. Now let's proceed. Let's load our data set. We're going to load two data sets here. One is the iris data set. The second one is the digit handwritten value that I showed you earlier. Now these data sets are described here. Or more like trying to describe what these data sets are, but I'm not sure these things are new to you, so you should be already familiar with how these data sets look like. Here is an example of the digits data set, and then you can see it's more like an array of 1797 rows and 64 columns. So now what you need to understand is this is an image. So it's a full array do represent an image, one image. So these are like sets of images. And then, so we have 1,797 images in this data set. And each of these images, they have been fully classified. So they are labeled. So the target here is more like the label. Oh, if you look at this thing you're looking at, you have a zeros, you have a one, you have a two, like that, like that, like that. Here is an example that shows you, that loads one of the data sets. This is the first row. And in this first row, it shows you, I think it was printed somewhere here. So here, so this is the value of the first row. You do this.images 0. This is slicing. I think you did this in list and then you did it in NumPy and the data and pandas and tutorials. You will see this. So this is a 8x8 image. So therefore this means that this array, there are 64 values in this array. Now we'll try to plot it. So remember, this is supposed to be a handwritten. So then handwriting, you have more like handwritten numbers. So barely looking at this, you can see that it follows the shape of what? 0. And that is why you see here the value, the first value here is 0. Now let's move forward. Let's try to define an estimator. In this case, we are dealing with classification. And we want to use the support vector machine. If you come here in this scikit-learn, you will see support vector machines here. You see they do have classification, regression. Now, if you click classification, it's going to show you this. And then it's going to show you how to call it from sklearn import svm. And then you define your estimator, svm.svc in parentheses. Now you have an X and your Y. Your X is your training data set, your Y is your label. And then you do clf.fit xy, and that's it. So they made it, these are very, very simple examples, but you can also follow these examples in your own notebook and play around. It's not going to cost you anything. All you just need to do is to open this and you start playing around with this. That's what some of you haven't done it before. But you can also follow the example here. Yeah, so now we do the same thing. But the only difference is that in our own case, we passed in the parameters. So for every every estimator that you define, they come with parameters. Now parameters is how to tune the algorithm to perform better or fit well for your data set. You understand? So it's just like maybe when you do settings in an instrument, you want an instrument, you want your PC to behave in a certain way. Maybe you want it to be brighter, or you want it to be dimmer, or you want the sound to be higher, or you want it to be lower. So this is more like a bit of what can happen in machine learning as well. And when you do this, you are good to go. You define your classifier, you pass in your data set, you train your data, and then you move. So these things have been well described. We've shown you this, and then here is the Iris data set. We basically do the same thing. Here we use the train, we load the data set, show you the features, more like the inputs and as well as the outputs, and also show you the properties of this data. This can help you see, okay, this data has to do with flower information. Yeah. And that's it. You define your classifier, define the parameters inside of it. So if you don't want to define these parameters, you can as well just leave it as default. Open the bracket and close the bracket, and that's it. But it's also always advisable for you to read through the documentation and understand what those parameters are and see how you can change them to meet your desired objective. So we'll define this classifier here. You can see it tells you the algorithms that have been defined. And then you train your X train and Y train, and you're good to go. Remember, we have used train text split to split the data set. Remember, I talked about text splitting data. So you originally have the data as X and Y, which we have defined here. These two here. And then now we use this there's a train test function to pass in the X and Y as this, and train this, and test size is telling you, oh, please I wanted to split this data into two-fold. I want the test size to be 20% of the full data, whereas the train side is 80% size of the data. It's going to follow that instruction. And then you also indicate random state. So the reason why we do this random state, it is not compulsory, but if you want to make your work reproducible, maybe, oh, you're doing this, and then you want, especially for those who are doing machine learning in the capstone, I recommend you also use random state. 42 is just one of those common, habits that we formulate. Everybody just want to use 42. So you can also use your own distinct value. But what it means is that any number you use, if someone else follows the same method, you should be able to come to the same, give you the same result. And that's it. You train your model, you perform prediction. Here we did the predict. We now evaluated the accuracy, and then it tells us, boom, that this is 100%. Remember I told you accuracy should go from 0 to 1. And well, this is beautiful, but in real life, it is difficult to get to 100%. And if you run, maybe you run your algorithm, it's telling you 100%, then probably something is off somewhere. Yeah, but because of time, we'll not be delving into all of that. You can see that every matrix here is all 1, 1, 1, 1, 1. It means that this model is too perfect, it's too good to be true. It's too good anyway, because this is a toy data set. So this is also an example of saving the model. So let me quickly rush to another example notebook here. So this is a case of real-world data sets. Now, in the real-world data sets, you've played with toy data set where you fetch a data from scikit-learn, and then boom, you train. Now, in this case, you have a photometric redshift of galaxies. Many people have been asking what sort of examples can you do in astronomy or machine learning. There are a couple of them. Some people do image analysis, some people do clustering analysis, some people do regression analysis, some people do classification analysis, some people do anomaly detection analysis. So there are tons of things that you can do. Here's an example of regression. You have a case of extragalactic astronomy where you are looking at the redshift of extragalactic objects, be it galaxies, be it quasars, be it AGNs, or whatnot. So the redshift tells you how far the object is sitting away from you, how far it is from you at the same time. Now, we have instruments like SDSS that has filters that can be used to collect this information. Magnitude. Magnitude tells you how bright the object is. And also the differences can also tell you how, when you compare, so if an object is a bit far away, the color value or the magnitude value will be changing a bit. So just because of time, I'm not going to describe all of that, because this is also written very well for you to understand. But one thing I want to emphasize here is that when you're doing machine learning, if you get access to your data, you need to do a lot of extra, what we call exploratory data analysis, which is what I'm expecting you people to do in your capstone. You need to understand, look into your data, try and understand what is happening in data. Is there something that is wrong? Is it in the shape or form that you think is adequate for your project? Or is there something that you think are not normal, and then you try and remove them? So I'm not going to talk about all of these things, but barely looking at this here, you can see that this is the original data set that was created. And then this data has been loaded and transformed. A lot of things have been dropped. And then at the end of the day, it has been prepared for you as a pandas data frame, which is what you have here. And then at the same time, we've created new features. Colors, these are called colors. For those of you in astronomy, you understand what we mean by colors. Colors is different between the observations made in two filters. So that is what we've obtained here. And the colors is what we are going to use to train a regression model that should be able to classify colors of an extragalactic object to tell what a likely redshift would be. And then here in this section, we just walked around doing this visualization for these properties. This is the visualization for the magnitude. And then this is the visualization, the plot for the colors. You can see how here it is quite spread. Here it's a bit thin and all that. And then this is the distribution of the redshift. You can see it flattens out. There are a few sources that are between 0.25 to where majority of the sources are dominated around 0.1-ish or 0.2-ish. So now we've seen this before. You use the train test plate to take the data, define your features, define your target, which is the redshift, define them here as X and Y. Yeah, so maybe you can notice something. We're using X and Y. Why are we using it? Remember, some of you must have done the normal mathematical function. X is equal to f of X. You understand? So this is an idea that your Y value is a dependent variable, and your X values are independent variable, right? So just going back to the basic mathematics that you've done in high school or in your early university. So it gives you, it kind of follows the same syntax. In short, it's the same syntax. Yeah. So just that your independent variables can be of multiple sizes, can be quite large. Yeah. And after training, you can see we now have roughly 10,600 sets of data for training, and then we reserve 6 for testing. And then here, before doing the training, you look at some evaluation techniques for regression model. This can be found in here. A bit of that information is also shown here in scikit-learn. But try to make this thing very relevant for you. But the good takeaway is that we have the root mean square error. We have the R square, which tells you how your model is performing. So if your model is, if your R square is tending towards 1, it means your model is learning quite well. If it's just around 0-ish to 5, it's not doing any better. Same thing for root mean square error. It should be decreasing as it's more like your loss, because your model is learning quite well. So the errors and the loss should be dropping. So that's it. Here is just the nitty-gritty helper function for you to evaluate these models based on the evaluation techniques that were defined up there. Thanks to scikit-learn, they actually do have functions that you don't need to start writing code to do this by hand. They already have these functions where written codes that you can simply use to do the evaluation. All you just need to do is to import them. And then here we import a couple of models that we want to try out. A couple of algorithms that we want to try out. Now we run these examples here, and then you can start seeing the results. For each of them, this is the example of linear regression, which I believe majority of you must have done linear regression. So I don't need to explain what linear regression is to you. I know you tend to do it, and then you look at the correlation coefficient, right? Good. So R square is also like your correlation coefficient. In this case, this performed poorly. You can say you expected to have this kind of line, but boom, this is so terrible. 0.45, so it's not learning. You can even see the prediction, true values and the predicted value. You can see that it's not following the pattern at all. It's not following, there is no relationship at all. It's just flat. You can see the residuals is very, very wild. It's not converging. And here's another example. This is a lasso, another type of linear regression called one where you have L1 and L2. They're basically the same thing, but this is a case of you maybe penalizing certain parameters in the linear regression. So you can see that all the linear regressions are terrible, the same behavior. And then for ridge regression, we're also seeing the same behavior. For k-nearest neighbor, we can see that the model did quite well. The mean square error dropped, and then the R square did perform quite high. So you can see in the fits that, yes, this is really, really tangible. But however, there are some of the data set that it was unable to predict. But this is also what happens because, like I said, you never get perfect model, but it's also good for you to train your model such that it can improve, can be efficient. And then we have this, and this is for decision tree. It also did quite well, but you can notice this is pattern. You can see that this one is way better. K-nearest neighbor is way better. Decision tree is learning, but there's also a lot of things going on in the model. And random forest did quite well, just like a nearest neighbor, quite similar in its behavior. So what Vector mentioned, well, to a great extent, it did quite well for predictions that are probably less than, say, 2 redshift, but did very poor for other ones. Yeah, so you can see how some of these algorithms behave. And then here I talk about the feature scaling. So I'm going to leave this because I understand that Priya is going to talk about it later, but I've also defined some parameters for you, which can also be called right from scikit-learn to do all of these things. We have different types of feature scaling. Feature scaling is you taking your features or your training data sets and then you normalize, you try to scale them. So you can also scale. This is maybe when you don't know exactly what to do. If it's a domain data, you can also create your own features. Just like in this example, we created our own features, which is the colors. We created new features. So we have an aspect of machine learning called feature engineering. So feature engineering is when you try to do a lot of related data analysis, looking at the distribution and think, okay, maybe if we plot a data set and looking at the distribution is looking weird, what can you do? Do you need to log it? Do you need to maybe do some arithmetics to see if you can be able to create a good distribution? Because it is very often advisable for you to look at each of the features to see how you can normalize them. Either they have a normal distribution, you understand, or you scale them to see if they can be close to a normal distribution. Because the better you do it, better your features are in that distribution. Better you, if your features are following that sort of distribution, the easier it will be for your model to learn something from the data. Yeah. So this is one example where we did standard scalar and we tried it with the same data set. So we took our input data, we just transformed it, and we did this after doing that. There isn't a lot of changes, but you can try in your notebook. You can also try these other examples here where you can do min mass scaling. You can also do to try out these other ones. Information about them are available in this link. So I'm going to end here. The fourth notebook is about hyperparameter optimization. So it's about how to tune a model. Now we've talked about these models. You just call them, but how do you play around them? How do you change these parameters or constantly change to see the ones that will be very ideal for you? So that is what this notebook is doing here. It is quite detailed, not that lengthy. Yes, so but I will also advise that as you read through, please also check out the links that have been provided, or also Google some of the terms that have been used. It is going to help you understand this way better, unlike maybe just relying only on the notebooks, especially if you're a newbie in this area. If you're a newbie, I'm quite sure you might struggle because these are not some terms that you know, but take your time. It's not ugly. You just need to follow through, do some reading. This is basically the same data set that we had earlier. We only just did parameter tuning where we used things like K-fold methodology. We did cross-validation. So initially, like in this example, the K nearest neighbor, if you remember in the other example, we used things like 3. Here we've defined list of numbers from 1 to 50. So you said, please try things like 1, 3, 5, like that. So it's going to run through all of this. For weight, try uniform and distance. For P, try 1 or 2. In the description, you're going to see a lot of these things in the documentation and the explanations for each and one of them. Then the K-fold will now say, oh, I want you to run this thing for split this data 20 times, partition so from that data, and then keep running each one set and see in all of this which will be the better option or which will give you best result. So you define your refit is more like the evaluation method that you are prioritizing for this very method. So I've used up my time. We're supposed to just spend 1 hour here. So apologies, Priya and Najam. So we played around with this with for k-nearest neighbor regressor and random forest regressor. So it's just the same data set that I've described earlier. So here, there's nothing, there's only introduction is just trying out the cross-validation methodology. So I'm going to stop here. And please, if you have any question, leave it in the chat here, and then I'll respond to them while Najam and Priya continues. Yeah. Hi, Najam.
Yeah. Hello. Thank you. So it's after a very comprehensive talk by Daniel on machine learning. I'll come to specifically machine learning in astronomy. And machine, as we know, just a minute, I'll just. Yeah, so machine learning in astronomy. On this first slide, on the left-hand side, you see a graph which shows the number of articles on astronomy which have been increasing since or after 2000 and all the way up to 2024. And you see there's an exponential growth in the number of articles which are coming out. In this graph, the blue portion of the bars indicate articles in astronomy which have machine learning and which is being used, and we have major astrophysical journals, and you see that there's a tremendous amount of increase in that. So we are living in times when astronomy has moved on from a data poor to a data rich science. There's a flood of data which is flowing in. In 1990s, we were dealing with data in megabytes, and in 1990s, it went into gigabytes, and 2000, it went into terabytes, 2000, it went into petabytes, and 2020 onwards, it's going to exabytes. So there's a tremendous amount of data coming in. It's because astronomy is essentially dependent on technology, and as technology is changing, we are getting more and more data. We have moved on from naked eye astronomy to those with telescopes, with CCDs, with large astronomical surveys, virtual observatories, and now we have LSST and SK and all, where there's tremendous amount of data coming in. Hence, it has become essential for astronomers to handle the big data sets and interpret these complex physical problems by using sophisticated statistical techniques and technology. It's become essential to use programming languages, whichever it may be, whichever it suits you. So it could be C, it could be Fortran, but the present trend is a lot of astronomers are moving towards Python because there are a lot of uh, libraries which are being created and being shared and which are which are of great help in handling large data, and right. So hence this whole workshop is centered mostly around Python. So as we collect these huge amounts of astronomical data, it has gone beyond human capacity to analyze without help of machines. And it's become essential to train computers, train machines to sift through this data and identify patterns and find connections that might otherwise be missed by humans because of the immensity of data. And this process is called machine learning, and it is an essential aspect of modern astronomy. So what are the things which we, so before we get into the basic problems of astronomy which we can handle, and what are the aspects which we try to tackle in astronomy using machine learning, just another slide. that 1950s to 1980s was where early artificial intelligence stirred excitement. 80s to 2010, machine learning begins to flourish. And we are living in an era beyond 2010 to present times where deep learning, breakthroughs drives the AI boom. And on the top, you'll see this machine learning, deep learning, and AI being have applications in 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 all walks of life of human endeavor. It could be email spam and malware filtering. It could be traffic production. It could be automated language translations and online fraud detections and so on. And we'll be more interested in astronomy. So the types of machine learning, we can broadly classify them in supervised, unsupervised, and reinforcement. In supervised, we have a training set which is used to train um, the machines, and then for the unknown, the other set, which we have no idea about, it sifts through it and finds out closest match, sees similar patterns, then um, and classifies them and so on. So basically, as in astronomy, there are innumerable way situations where machine learning and AI are being used, but which we shall see now. But very broadly, we use techniques of regression, correlation, regression, and so on. The second one is classification and clustering, right? Apart from that, you will see that it is being used in image processing. It's being used to detect very faint signals which would be missed out, like detection of gravitational waves and so on. So classification, when do we do? Yeah, so basically, when we have, say, when we look at galaxies, they come in a variety of shapes. Some are spiral galaxies, some are lenticular galaxies, some are very filamentary disk-like. You have some with bars in it, right? So there's a whole zoo of galaxies, and they get, and as human nature is, when you have a variety of certain things, we start classifying them. So one of the very popular classification is of the Hubble classification of galaxies, where you have ellipticals, you have spirals, and you have spiral with bars, and you have between the ellipticals and the spirals, you have the lenticulars. And you have in spirals SA, SB, and SC, and which essentially goes from the central nucleus being very large in SA, becomes smaller and smaller as you go from B to C. And the spiral arms are tightly wound in SA, but they open up in SC. Similarly, you have spirals with bars A, SBA, SBB, SBC. And these classifications are very commonly used. And you have the ellipticals, which are E0, E1, E2, E7, where E0 is a circular one, while E7 is the most um, um, elliptical one. So from the change of ellipticity, you go from E0 to E7. And in between, you have these lenticular galaxies, where it shows a big bulge. It has a featureless disk. So it lies somewhere between. It looks like an elliptical galaxy, but with a bar. So the moment you see, um, the moment we have a zoo of galaxies, we would like to um, classify them, and computers are being used to do that. So initially, the training sets are created by humans. Humans are also trained to define between an SA, SBSC, or what is a barred spiral, what is a ellipticals. And these are used as training sets to train the machines. And since we have observations of billions and trillions of galaxies, the machines see the pattern and classify them. So this is somewhere we use. So classification is essentially a supervised way of putting them into different bins, right? So for example, we have these light green and blue dots, and you define some parameter by which you segregate them and you classify them. You classify them as with spirals and lenticulars or so on. Okay. The other important thing which is used, which is very close to what classification is, clustering, which is an unsupervised uh, machine learning technique, where you define certain parameters which define groups, or you may not know what those parameters should be, but the machine tries to look into the large amounts of data and tries to see similar patterns in different sets and clusters them into different clusters, right? So Priya will be handling examples of clustering for membership determination and star clusters. Now, another thing is if you have a relation, you have a dependent variable and an independent one, and you are interested in finding the relation between that, right? So this is usually goes where you have continuous values, for example, as age and redshift and so on. And for example, if you are looking at galaxies at different redshifts, which indicate different distances from us, and we want to see the velocity of recession, the redshift. And like Hubble and Emerson had found that the more distant galaxies show a greater velocity of recession. The ones which are closer show less. So there is a linear relationship between that. So one tries to find a relationship between that, and that relationship is given by this regression line. And so regression line essentially is as you have a set of data points, a scatter of points, and you try to find a straight line which fits the database, which is the best representation of the data. And this is done by various techniques. One is you try to minimize the distances of these points from the predicted line. And you keep adjusting the line till the time the differences become minimum. And another one is the least square approximation, where you find the squares of the deviations as predicted by the regression line and the actual ones. Take the squares of this and you minimize the sum of these squares, and that will give you the regression line. So, and finally, the regression line gives you a equation of a line which gives some kind of an empirical relationship between the dependent and independent variable. If you have more than one independent variable, you could have you try to find a plane, or you where uh, uh, where this dependent variable and between the independent, you try to find a relationship between this. So you, instead of linear regression is what we generally use because it's the simplest, but by looking at the scatter and looking at the data, you sometimes fit an exponential curve, you can put a logarithmic curve and so on, right? So it's not necessary that we only have linear regressions. It varies. So coming to uh, one more example, there are stars, as we know, which show variability. There are stars which become bright, and over a few uh, days or weeks or minutes, they increase their brightness, become very bright, and then they start becoming fainter, and then it rises again. So this variability in stars could be because of some intrinsic phenomena. With the stars itself has some certain physical processes which are going within it, which makes it flare up and then make it come down. Or there could be an external extrinsic relations. For example, there can be two stars and they are eclipsing each other, and sometimes we see both the light coming from both the stars when it looks bright, and as one star eclipses the other one, the intensity drops down and then it increases again. So you have these eclipsing binaries, or you can have rotating variable stars and so on. So you see on the left hand side there yeah, so again, the pulsating stars are of different category. Each one has a different signature. You have C-feed variables, you have RR Lyrae, you have RV Tauri. All of them have different kinds of light curves. And by classifying, by looking at it, right, again, the C-feeds are type 1 classical, type 2 Virginis, and so on. And long periods have Mira types and semi-regular. And eruptive and cataclysmic stars are, they are supernovae, they are blowing up, or they are novae, or they are recurrent novae, dwarf novae, and so on. And each one has its own signature and a different light curve. So on the left hand side, you see light curves of various stars, and you see that profiles vary tremendously, right? And each profile is an indicative of what kind of star it is and what kind of physical phenomena is taking place within it, and hence you can understand everything about the star as to what processes are going on now and how long will it live and how will it blow up and when. So you have tremendous amount of data on stars and their of variable stars and their light curves, and it has become very difficult for people to sit and fit these curves to each set of data and decide what type of a variable star it is. Rather, these machine learning techniques have become extremely helpful and good in doing it. And you can get a wealth of information from these light curves. You can understand, say, in eclipsing binary, you can find out what are the sizes of the star and what are the orbital elements, how is their orbit inclined, what is the eccentricity of the orbit, what is the, all the details. So if I'm looking at these, we can find out much about. Yeah, so here are examples. Similarly, we have exoplanet discoveries where you have Kepler 4b, 5b, and you see the light curve as the object, a planet comes in front of the star. There is a small, very small dip in the intensity of light, and then it again rises up as it goes past. Because at this stage, when it is um, going, occulting the star, it's going through the line of sight of the observer and the star. There's this black object in between, opaque object, and there's a um, dip in the light intensity. And depending on how big the drop is and for how long there's a change in this, we can understand from which part of the star it's moved transiting, what is the size of the planet, and various such features. So by looking at these dips, we would decide whether uh, it's a planet or it's not. And since these drops can be extremely minute, it can be missed out by humans, but machines, if they are well trained, they can sift through this data and find out the candidates of those stars which show this kind of variability. And it gives us a chance to look at them in a more organized later. Yeah, so we get, you have spoken about the regression where you have, for example, we have distance on the x-axis and speed on the other one. You are looking at the velocity of recession of galaxies, and you see the redshift, right? And you see that there is a relationship between them. And this line gives you the relationship, what it is, y equal to mx plus c. So the slope of the line, how deeply it is inclined, or how at what angle it is, how steeply it is rising, shows you the relationship between the two. And we could be interested in looking at galaxies and their velocities, and which had led to understanding the expansion of the universe. But there can be many other relations you may be interested in knowing. For example, looking at the metallic content of galaxies and its relation with redshifts. So are the galaxies which are further off, far off, they are metal poor, and the ones in neighborhood close to us are metal rich or not? And to find this kind of a relationship, we can use a regression, and or it could be star forming rates in galaxies as the distance. So uh, so it has been seen that there is a certain redshift of 6, where galaxies seem to show maximum amount of star formation rates and so on. So seeing such relationships, so it could be an increase and then a drop again, or it can, right? So linear fits will only give kind of a relay relationship, but you can fit logarithmic fits or polynomial fits and so on and do it. And you can do that in with different wave bands to see what they are. One more interesting example is that of from celestial mechanics. So I'm giving you examples where machine learning is being used in variety of different cases, which vary totally in the nature and requirement. The three-body problem has to do with the study of motion of three masses under the mutual gravitation attraction. So suppose you have three masses, yes, and you know their positions and velocities at a given time. You know their masses. You want to predict how will they move in time, right? For example, you have Sun, Earth, and Moon are most important three-body system which affects lives on Earth. And we want to try how, what is the motion like? Will the moon always be moving around the earth at a similar distance, or is it drifting away, or will it come and collide with us sometime? So this is called the three-body problem. And strangely, the three-body problem has no general closed form solutions. The actual technique of handling this is write differential equations and solve them and predict the motion. But when you write different equations of motion for two bodies, you can solve them, and you can get a general closed form solution, which gives us those Keplerian orbits. It's either a parabola, hyperbola, or an ellipse. But if you have a three-body system, you cannot find a closed form solutions. And this three-body problem has been at the heart of celestial mechanics for over 400 years, and it led to development of a lot of mathematics like differential equations, stability theory, calm theory, and so on. And they are very beautiful techniques of studying regions of possible motions, regions of stability, and criteria which make systems stable or unstable. But the interesting thing today is, though this does not have a general closed form solution, which was proved in late 1800s that you cannot find a closed form solution. What's interesting now is machine learning techniques are being used to very beautifully get solutions to the three-body problem, right? So machines are being trained with various initial values, initial conditions and masses and so on. And on the basis of this, it can predict for a new set of initial conditions. And these machine learning techniques are proving to be much more efficient than the normal analytical methods or methods of solving these differential equations. So machine learning is even coming in areas such as these. Yeah. Here's yet another example, and I'll stop soon with this. We were all taken up by this beautiful picture of the black hole, and convolution neural networks were used to compose this image. And this image, which we see below, the donut-shaped image of a black hole, was these CNN convolution neural networks we used to reconstruct this image. The Event Horizon Telescope team developed computation imaging algorithms capable of making inferences to fill in the blanks and the data had not been gathered. So in regions where the data was not there, this was generated using these convolution neural networks, and this image was reconstructed. Now, new images of this black hole with magnetic lines and all have surfaced. So it will be a good idea for you to look at those beautiful images too. Yeah, so before I end and hand over to Priya, just a word of caution that there are various issues in machine learning, and you have to use, though it's a very powerful tool, but one has to use it with discretion. You should be careful, because you should not use it as a black box and make inferences which are absurd. So, what algorithms can approximate functions well and not, you have to be conscious about. How does the number of members in training sets influence accuracy? You should have a good understanding of that, right? So how large a training set should be, on basis of which we'll be making predictions, and integrating learning with systems, and what are the theoretical limits of learnability. These have to be kept in mind. And how do you transfer learning, and how do you get machines to have a system to continuously train to improve on its algorithms. This should be incorporated. Yeah, so with this, I will stop and come back to you later when we'll do specifically the Jupyter Notebook. Thank you. And over to Priya.
Yeah. Thank you, Najam. So I'm basically going to talk again about application level stuff with machine learning, because this would be potential stuff which you could think of for your capstone project. Okay, so I'm basically going to talk about a special case, which is the case with star clusters, basically because I work on star clusters, and this is work that we've been doing. We started this since some time, and hence these were good. You can hear it? Yeah. And hence these are good examples of things you can do, right? So let's just talk briefly about star clusters. So star clusters are basically building blocks of galaxies. And why are they building blocks of galaxies? Because essentially stars, we know that they form in groups. They do not form in isolation, they form in groups, form giant molecular clouds. And therefore what happens is that when these star clusters form in groups, right, they actually that's how star formation takes place, and this is how it builds up the stellar population in a galaxy. Okay, now you have typically 2-3 types of star clusters. You could have open clusters like the one below. This is the, for example, like the Pleiades, which, or Kritika, which we call in India, which is in Taurus constellation. It's visible nowadays. It's a naked eye cluster where you see it's often called even the Seven Sisters. This is another open cluster where you can see a group of stars. They are not so tightly packed together. On the other hand, you could have globular clusters, which you see on this upper right, which are more tightly packed, larger parts. And these two objects are quite different because the open clusters are basically make up the disk population of the galaxy. They are in the disk of the galaxy, while globulars are basically found in the halo of the galaxy. So essentially a cluster is a group of stars which formed at the same time, distance, chemical composition. They differ only in mass, right? So now comes the next problem, which is the problem of, which is the problem of membership. When I look at this group of stars, for example, in this image, how do I know which are the stars which actually make up this cluster? I can clearly see that there is an extra extra concentration of stars, but I do not know, for example, this star or this star, does it belong to this group or it doesn't, right? Because there could be a good number of stars which are in the foreground as well as in the background, and I do not know which ones make up the cluster. Now, the answer to this question came up very recently with a very good satellite, which is called Gaia. You'll have already seen what is Gaia data. So Gaia is basically a satellite by the European Space Agency. And what it basically does is it basically very accurately measures the positions of stars, okay, which is called astrometry, the positions. And because it very well measures the positions of stars to the accuracy of a micro arc second, okay, because of that, what happens is that it can also detect the motion of stars, because so this motion can be even the parallax. The parallax is the effect you're getting because what you're seeing with two eyes, you see a certain angle and you use this to measure the distance to an object. Similarly, if you can see this different or the shift in the position of this object with time, for example, in a year, you see it in January somewhere, and then you see it in July somewhere, and you use that to find out the distance, because the distance would be 1 upon parallax. So what we do is Gaia therefore very accurately measures the parallax of these stars. It also measures what are called the proper motions. That means in the plane of sky, I can actually detect the motion of stars. Now, generally, the motion of stars in the plane of sky is very, very slow. There's a very small motion which is almost undetectable. Therefore, we think that they do not move. But actually, if you were to accurately measure, there is a movement, and that is measured by Gaia. So Gaia basically gives you six-dimensional data. It gives you the right ascension, the declination, that is the coordinates of the star. It gives you the parallax, that is the distance of the star. It gives you the proper motion in RA and proper motion in dec, which are the velocities. And for the brightest stars, which are brighter than 14th magnitude, it has a spectrometer, which will also give you the radial velocity through the Doppler shift, right? So this is a very revolutionary satellite which has totally changed our understanding of the galaxy, the structure of the galaxy, the kinematics of the galaxy, and in that sense, it's a very important thing. Now, this is the data set we've been basically using to find out membership. How do we find out membership? That typically if stars belong to a cluster, they will all be at the same distance, they'll have the same parallax, they will also have the same proper motions in RA as well as in dec, and even the similar radial velocities. Chemical composition can be done also with Gaia data, but then that is done with ground-based telescopes. If we have spectroscopy of these stars, we can also assume that if they are from the same molecular cloud, they have the same chemical abundances. So if we measure the chemical abundances, we can actually match stars because they have the same chemistry, because they belong to the same cluster. Okay. So this is exactly what we tried to use with our machine learning techniques, because what happens is with Gaia, when you're looking at a certain part of the sky, you'll see thousands of stars. Now the question is, how many of these thousands of stars actually belong to the cluster, right? And that will define which ones are the members. So the first technique we used is the supervised learning technique. It was already been explained to you that the supervised learning technique is a labeled technique. So, for example, you were already told by Daniel, for supposing you have images of dogs, you have 100 images of dogs, right? And these are dogs from different angles, from different kinds of dogs, etc. You have these 100 different images. Now, based on this, you train the data set to kind of define what does a dog look like, right? So then if you have a set of say 10,000 other images, because you've trained the system with recognizing dogs, then when you have 1,000 images, the system should be able to recognize the dogs in that, right? Now, one of the biggest problem in machine learning techniques is validation, right? Because the problem with machine learning techniques is that you can put in whatever algorithm you want, you will get an output, right? You will get an output, but the question is how correct is your output, because there are many, like Najam sir mentioned it to you, if you use it like a black box, right, where you're just using it to give in an input and get an output without understanding what is actually happening, then you could have your output being absolutely wrong, right? It could be a totally wrong output, and hence you need to understand the system. People doubt if you generally typically send a paper for publishing, the referee would definitely doubt what is your result. Now, the advantage with the supervised technique is that the process we do, which is it's called validation. How do we validate our data? For example, supposing I have these 100 images of dogs, right? I only use 70 images or 70% of the data to train my set. Now, 30% of the data, I know which are the dogs, but I add that to my sample of 1,000 images, right? And then I check how well do I retrieve the data for the 30 for which I know the labels, right? I know they are dogs for sure. So then I check that for my 30, my system, how often does it recognize, maybe it recognizes only 27 of them to be dogs or 25 of them to be dogs, or maybe it could even just do 10 of them which are dogs, right? So that shows me how badly my system is retrieving the data. If I get only 10 out of the 30, that means 1/3 of mine are only correct, but I have a lot of what we call false positives and false negatives. Okay, so you could have both these kind of things, false positives and false. I'm sure with the pandemic, people have already used these terms of what are false positives and false negatives, and you'd understand what that is. So this is the advantage of supervised technique, and the one that we used is what is called random forest. You can read about it on the net. What is random forest? So we took a sample of 9 open clusters which were located at different parts of the galaxy, different latitudes and longitudes, with a different age range as well as different galactocentric distances. So they were well spread in the galaxy, so that I don't have a bias because of their position in the galaxy or their age or their size. So there is an earlier paper written by Cantat Gordon which actually gives membership data for stars up to 18th magnitude. Okay, because this was basically done with DR2, the data release 2 of Gaia. So they did it for that. And what we did is we actually trained our data. We retrieved the data for these clusters for a radius which is double that of what was given by these authors. We took double because you could have a good number of stars in the outskirts also of clusters. And then we use this training data set with random forest and this thing. Just to let you know, all the stuff we used in this is basically work which got published in 4 different papers. You can have a look at them at the net. There's this lower one over here, but the other ones are also there. All these papers are basically using machine learning code which is there in the scikit-learn package. Okay, that is what Daniel spoke about today, the scikit-learn package. And basically the scikit-learn package has code for all these different kinds of techniques. For example, if you want to use k-means clustering or random forest or the other ones which I'll talk about, we just use scikit-learn for all of them. So we use random forest, and here you can see our results. Orange are the stars which were there for the training set. Blue are the stars which we retrieved. And you can see that the number of members has very drastically increased for all these clusters. We also have some more interesting. Here you can see this is the histogram. The orange one is for the training set, the blue one is for the extra stars, and the green one is for the total sum of stars which we found, which kind of you can see that the peaks coincide with that for the training set. So we are keeping up the characteristics of the training set. What you also see very interesting is we actually end up with these substructures. What do I mean by substructures? For example, if here you can see this is velocity space, this is proper motion in RA and proper motion in DEC. This is the training set. This is our additional stars, and then we end up with this. So now you can see that in velocity space, we are actually getting these substructures. That means I can typically the cluster stars have to be located at this thing, but I'm also getting another region where I can find some more stars which belong to the cluster. So you can see that there's a slightly substructure which is there in these galaxies. Okay, sorry, in these star clusters. Also look at the color magnitude diagrams. If you see the orange ones, these are the ones that we used for our training set. But the ones that we derived, if you remember, this thing, when we run this code, we run it basically for proper motion, for positions, proper motions, and parallaxes. But we do not use it for photometry. So when you see structure in photometry, that is not coming because of the machine learning technique. So now you can see that these stars which are sitting over here, for example, these regions, these ones are the ones which are being identified by our technique. Some of them are variable stars, these are pre-main sequence stars. They've not yet come and sat onto the main sequence. You can also see that there are what we call blue straggler stars, which are above over here, or you can see there are some more stars which are, not exactly not sitting with the CMD, but sitting in this region, but they are members, right? So we do see a lot more, this is what we'd call an enriched color magnitude diagram because of this thing. Okay, so this is the validation. We've done it with 30-70 ratio. This is the standard thing. This is the kind of data we got. These you can see all the details in this paper, which I showed it to you. If you just Google Priyasan or whatever, you'll find it. Okay. So this was the paper which was published and which we this thing with our students. Okay. So the other important thing is that one of the problems with supervised technique is you are dependent on your training set. Supposing there are any mistakes in your training set, then you will not be able to identify your members correctly. And hence we use some other techniques which are unsupervised techniques. That is, we do not have the labels. We are not assuming any membership data. Only thing we just have our 5-dimensional data, and what we assume is that if these stars belong for the cluster, then in this 5-dimensional space, which is basically made up of RA, deck, proper motion RA, proper motion deck, as well as parallax, right? In that 5-dimensional space, these stars should be close to each other, right? Because they are in this they are, belong to the cluster. So there are different kind of clustering techniques which are used, but we'll focus on some. The question is, we use basically Gaussian mixture modeling as well as DB scan. And let's see how it works for all clusters. The big question in this is obviously what is the field to cluster ratio, right? That means in that part of the sky, how many of the stars belong to the cluster and how many do not, right? That's the important thing. Okay, so let's look at Gaussian mixture modeling. Supposing I have these group of stars, which I'm looking at, okay? If I assume that this set is made up of two Gaussians, for example, this is one Gaussian and this is the other Gaussian, right? I have two Gaussians, the blue one and the red one. But when I look at it, I see the combined effect of both these groups, which is the green. Okay, but I can break it up into two Gaussians and I can find the centroids of these two Gaussians, and in that way I can identify groups. When I do it for star clusters, it becomes more complicated because the field stars and the cluster stars are actually sitting with one another in the same location. They are not separated so nicely in RA deck, but they would be separated nicely in the space made up of parallax as well as in proper motion RA and proper motion deck, because we are looking at a 5-dimensional space, right? So in that case, you will get this good thing. So we applied Gaussian model, and this is one of the clusters where we got one of the best results. You can look at this. This is a cluster called M67, and you can see that when we applied Gaussian mixture modeling, we got it that it's made up of two Gaussians. One is the red one, which are the cluster stars, and the blue ones, which are the field stars. And you can clearly see that the red one is peaking very clearly at a certain parallax value, which corresponds to the distance of this star cluster. And therefore, you can see a very thin, nice peak, which is coming up, which is the cluster stars. The field stars are randomly distributed, and therefore the Gaussian which you get for the field stars is more broader because it almost covers the whole area. So you can see there's a broader area which is for the field stars, and this one is the one which you're getting for the cluster stars. So if you plotted the CMD of the cluster stars, is a nice neat one which you can see in red over here. You have a very nice binary sequence also coming up over here, but over here if you see there's the field star, it's kind of a smudge. It kind of resembles an HR, but it's not. So again, we did this for a large set of clusters, and we actually got the number. We compared the number we got with Gaussian mixture modeling to the number which was there from the training data set, which was used for random forest, and we got an improvement of 2 times, 3 times, whatever, a larger number by getting it. We also actually get deeper. This is anyway going deep only, so we got this thing, and we used a certain metric called modified silhouette score also to see how well does it do it, because like I told you, a very big problem or a very big thing to focus on in machine learning data is whatever result you get from machine learning, you have to validate it in some way. It is easier in the case of supervised methods, but in unsupervised methods, you have to do other ways. So we use this thing called the modified silhouette score, which is described in our paper. And we also use spectroscopic data. So there are ground-based surveys where we actually have spectroscopy of those stars. That means we know their chemical composition. And here, if you look, for example, for a given cluster, this is the one which we had for the training set, which we knew. And this is what we got using our analysis. This is for 2 clusters. You can see up and down, these ones are pretty similar, which shows you that the chemical composition also that we derived for the stars of a cluster quite resemble the values which we had for the training set, right? So this is the same cluster with the training set, and this is the cluster which we got with our members. This is another cluster. So this is a lot of focus or importance has to be given to how to validate the results which you get from your given machine learning technique, right? So that is something which you really need to think about. There's also a method for Azteca. I'll skip this. So we actually improved the membership of these clusters, and we got identified various variable stars, etc. Another clustering technique which is used is called DB scan. Look at this star. Supposing I draw an epsilon radius around it and I say minimum points are 4, I have 4 points which are there. So this I call it a core point. I do that for every other point over here. I draw an epsilon radius and I check that within the epsilon radius, do I have 4 stars? If I have 4 stars, I call it a core point. Okay, this point falls in the epsilon radius of, for example, this star. So, but it does not satisfy the condition for a core point, and hence this is called a border point. Okay, so core points have an epsilon radius where you have minimum number of points. Border point falls in the epsilon radius but does not satisfy this thing. This point, for example, in an epsilon radius, it does not have the minimum number of points, nor does it fall in the epsilon radius of any other star. And hence this kind of point is called a noise point. This is not part of any cluster. But like, for example, these guys are all part of a cluster. This guy also belongs to this cluster, but it's not a core point. Okay. So for all points, I can define what are called core points and border points and noise points with DB scan. And with that, you can identify your clusters. The tricky bit, so we did it. This is also a paper which has been published, and you can have a look at it, see how it's actually done the analysis. Again, the same convention. The green one, the orange one are the ones from the training set, just for comparison. The green is what we got. You can see we've gone much deeper than the training set in our CMD, in our color magnitude diagram. This for the same cluster M67, which is NGC2682, and you can see the differences. Okay, we also compared our results with the spectroscopic data, that is the chemical composition of our stars, and we can see that it satisfies it pretty well, which basically indicates that the members we've got are good. We also use this to find out parameters. So these were done for various clusters where we found out these things, right? So you can have a look at this paper too. So as a capstone project, you could maybe run DB scan, or you could run Gaussian mixture model. This has been done for a select sample of clusters, but you can do it for a larger sample of clusters, or look for any region of the sky and see if there are clusters over there. So people use it for various things. Number one, to study clusters in more detail, or even it has been used by people to actually look for clusters in other parts of the sky, right? We also do this to study star-forming regions. This is also a published paper. You can have a look at it. Google Serpents and Priya Hassan, you'll find it. So in this, what we did is we looked for young stellar objects which are there in the star-forming region. We matched it to Gaia data, and you can see the modus operandi. We used YSO sample from other data sets, cross-matched it with Gaia. We get the parameters, make a control sample. We used machine learning techniques, DB scan, optics, HDB scan, and we used that to actually find it. So this was the thing. We queried a 2-degree radius. These are just parameters of Gaia data, so I won't go into details. This basic Rouvet factor tells you whether it's a single star or no. We now know the range for proper motion array, proper motion deck, and parallax. We use that to the problem is you do not want to have too many field stars. Okay, so it's always good to filter the data before you start. Otherwise, again, that applies to Gaussian mixture modeling also, that you need to filter your data a little bit, because otherwise your cluster stars will be, embedded within the field stars. You won't be able to see the cluster stars at all. So it's good to filter the data, take it within a certain range when you know what the range is. And we know that range because we have queried and cross-matched with Gaia data. We've got the values. So what we did is we then used this to find out a large number of young stellar objects. We had, how many were the 86 or something like that. And now we ended up with 822. We had 87, then we finally ended up 822. This is the paper that we published. and you can have a look at it. And we use this to classify the young stellar objects because we matched it to 2 mass and WISE data, and we got this, and we did this. And so those are possible capstone projects. I will also very fast. I'm sorry, but we are really running. We have a problem with time. But the advantage is that you actually have all these notebooks with you. So I'm going to show you a notebook, which is this one. It's okay. Yeah, so you can see this notebook over here. You can see this is a small notebook on running scikit-learn. Some of them have been done by Daniel, but you can have a look at it over here. So if you actually see, this is pip install scikit-learn and pandas, etc. K-means clustering. Here's a very simple thing where we've actually generated artificial data. There is a task called make blobs. So we actually made blobs. These are the 3 blobs. And then we use K-means clustering to actually find this thing. But just to play around with it, here you can see I've put n clusters 3 because I can see there are 3 clusters. But you may have to play around with the number of clusters when you are doing with actual data to finally come on to the correct number of clusters. But obviously you do that by visually inspecting the data to see that the number of clusters that you are asking it to fit, are they correct or no. So K-means has a very simple algorithm. That means if I say, for example, it fixes up how many stars do I want to actually find the cluster. Okay, here you can see the code for dbscan. Like I told you, it's just there straight away in scikit-learn. So in scikit-learn, there is something called a cluster. So you can import from scikit-learn cluster, you import dbscan. dbscan has 2 parameters which are crucial. One is called the epsilon, and one of it is called the minimum samples. So if you remember, what you're doing is that for every star, you're drawing an epsilon radius, and you're checking whether that minimum number of stars are there in the epsilon radius. So you draw this thing. And for example, here I put an epsilon radius of 0.8, minimum sample 5. And if I run this, it will actually identify which is this. Oh, I think I didn't run the earlier one. Let me run this earlier one. This is the make blobs from X, which now I used over here. I can play around with my epsilon value. For example, suppose I make my epsilon very small. Then what happens is, you can obviously see it. If I make epsilon very small, and I'm saying my minimum sample is 5, right? Then obviously I will not be able to find these number of clusters. Nobody will be a cluster. You look at this. These clusters are very, very small. Basically because I'm taking a very small epsilon radius and I want 5 stars to be inside that epsilon radius. So you see, I'm not correctly identifying it. On the other hand, if I increase my epsilon very large, right, and then do it, right, then in that case, it's not too bad because my minimum samples, but supposing if I make my minimum samples 25, right, I increase that. I've increased my epsilon sample and I've also increased my minimum cluster. If I do this, you see that, okay, this is not too bad because these are quite well spread out. Let me make this even bigger. I can make this, for example, I'll make it 55, for example. Yeah, you can see none of them get identified. Or yeah, you can also, there's nothing that epsilon has to be less than 1, for example. Supposing I made epsilon 3.9, minimum samples 5. Then what happens is all these stars are part of clusters because you have epsilon so large and your minimum sample is small.
15.
Okay, let's try it out with 15. 3.9 and 15. What do you want?
Epsilon.
Oh, you want epsilon to be 15? Okay. Let me make epsilon to be, somebody wants me to make it, okay, 23.9. I made it very big. So now all of them are part of the same cluster, right? So you see that the important deal in this is how do you play with the values of epsilon and minimum samples. If it's too small, you'll get very small clusters. If it's too big, you'll get everything as part of one cluster. Now this is identifying all these things to be part of the same cluster, right? So you have to play around with this. The paper that I showed you that we did on dbscan actually has some details on how do you actually optimize your value of epsilon and minimum samples because it's not too trivial. Okay. Here we've also done random forest. You can do random forest where I don't have too much of time, but you can run this yourself and see how you can actually run random forest. And you can see when you run the code, you run it and let me know if you have any problems. And what I wanted you to see, okay, regression. You were already told about regression for redshift estimation. right? So this is just an estimate magnitude versus redshift, okay? So you plot that and you try to fit this curve. If you want to fit it to a straight line, it's called linear regression. So then what you do is you actually, we have generated, this is artificial data. You can see X is a random number, and you're taking this for the range of magnitudes, and the redshift is also a random number, which I'm getting from here. And I'm doing a linear regression thing. If you see, I've even added some noise, which is the NP random. This is the noise, which is redshift with noise. So you see, when I'm fitting it, I'm getting this kind of a broad shift. Okay, if you're getting too big a broad shift, you may also think that maybe I should not fit it to a straight line. I can maybe fit it to a polynomial. So for example, here there is a polynomial regression one. If I want to fit it to polynomials, then I may fit it to a whole bunch of polynomials and look for that and see whether that fits better. So there are some assignments meant over here. For example, you can try k-means clustering on for SDSS data, star galaxy set. You can do classification for these things. You can use random forest. SVM, Nanam will talk to you about, but you can use that. You can do redshift prediction for some data set and use these various things. There are some things which you can read and have a look at it, and do ask me if you have questions on Slack. But now we'll do a very short thing which will be on SVM, which is for supernova classification. Yeah, over to
Yeah, thank you, Priya. I'll take a very short time to introduce you to this um, notebook. Where did it go? Just a minute, I'm trying to find the notebook. Yeah. So I hope you can't see, right? I'll have to. Yeah, so SVM is support vector machine, and basically it is used for classifying. Priya has discussed random forest and various ones. And SVM, you can go through this notebook and see. I'll just touch upon some basic things in this. So in this notebook, we are looking at classifying supernovae. So you have supernovae. What are supernovae? Stars as they evolve, and the massive, they evolve going from main sequence stage to um, giant, and then they blow up as novae or supernovae depending on the initial mass. And massive stars, which are say 8 to 10 times more massive than our sun, they become supernovae. They fuse hydrogen to helium, helium to carbon, magnesium, oxygen, all the way up till iron. And when the core is rich in iron, when it collapses and blows up, it ends up, this happens only for very massive stars. They end up as supernovae. Now, these supernovae again are of different type. You have type 1, type 2, type 3, and so on. And within type A, 1, again, you have type A, 1A, 1B, 1C. And this comes from basically supernovae which there's no hydrogen, it's type 1. When there is, it shows up hydrogen, then type 2. If it is electron capture mechanism, then it's type 3. Similarly, in type A and type B supernovae, which are type A, 1A, they show strong absorption bands of silicon near 6150 angstrom. And type 1B supernovae are formed when the core of the massive star collapses under its own gravity and so on, right? So basically, there are various features, and this is where SVM comes into useful, because For high dimensionality, it works very well. Yeah, when there are many features in it, right? When you have multi-band photometry, you are looking in different wave bands and so on. You are looking at different things. So when there are many features in it, this is when this classification using FVM comes in. And it is a very robust technique. And it is when there is non-linearity too, it captures it very well, right? So in this, you will have a look where where does it peak in U, G, R, I, or Z band? It makes a difference. The decline rates of these supernovae are different. The colors may be different. The spectral line strengths of silicon H alpha emission, right? So when there are many such features and you want to classify, then SVMs help well. So in the first part of this thing, we are constructing uh, uh, artificially data. And first we set up the libraries in the usual way, what Daniel showed, import numpys, NP and matplotlib and all those things. Scikit-learn, right? So Scikit-learn has scikit-learn.svm. We are importing it SVC, and we are creating sample data by NumPy random seed 42. And you'll notice, like Priya said, for some reason we are using 42 all the time. There's something sacred in astronomy with 42. And it is classifying into two types, type A1 and non-type A1 types and so on, right? And so you have training split cells and you run through this and understand what it is going. An important thing is also to look at this confusion matrix. So this tells us the one on the left hand side is the true positives. Numbers are 95. And this is false positives. There are only 4. And this block shows false negatives, and this is true positives. So numbers which are there indicate how good your model fitting in. So here in this case, our confusion matrix shows that true positives, they are 95, while false positives, they are only 4. So this indicates that the model fitting which we did for this data which we generated is pretty good, right? So these confusion matrices are good. And similarly, you go through these other parts which even Priya has shown. And I have a little bit of code below here where instead of just having whether it is type 1A or not, we are having many more in that. We have various classification and we are plotting the different type A and peak in U magnitude, peak in G and so on. And this gives you the whole analysis of the whole thing, which shows you, yeah, you have, if you remember, we have dealt with these box plots where the middle line indicates the median. This shows the quartile 1 and quartile 3. And the points above these two bars, these are the outliers, right? So these are very good ones. So in for type A1 and peak, you are in there are 4 outliers, while type 2 there are 1. So this gives you a very good analysis. And again, we have just constructed this. This code is just constructing this thing. Okay. So you can, as an exercise, you can add even more features in it. So add more features like hydrogen line strength for distribution type 2, include photometric errors in it, add more rare supernova types, and right. So this is an exercise where you can play around with. And second part of the exercise is you try to classify supernova using this SVM, using real supernova light curve data which is available in archives. Yeah, so we are running out of time and we've gone, in fact, gone beyond the time. So I'll stop here. And if there are problems, issues, questions, do get back to us. We'll try to do that. Okay, Daniel, over to you.
Hi, Najim. Thanks very much. Thanks, Priya, for the wonderful presentation. Yeah, so not sure there's any question in the chat. So okay, Arjun was asking about random state. The random state is how you make your model
Daniel,
training.
Daniel.
Yes. Can you hear me? I can't hear you. Can you hear me?
And no problem. Priya was muted, so she didn't hear you giving the explanation. Go ahead, please. Go ahead.
Oh, okay, cool. All right. Yeah. So yeah, I was just saying, okay, yeah, I think Ankita has replied that. We do not have any further questions in the chat. So if you have any other question, do ask in the Slack channel. Also, I've tried to respond to all the questions I did respond to earlier in Slack. So please take a look at it. Again, let me reiterate it. The submission is Google Colab. So you just take your time, write your analysis, all of the steps that you have taken, your visualizations, your code. Just prepare everything there and run everything and ensure it is working before you submit. And we're going to share the web link. So the submission is going to happen through a web link. A web link will be provisioned later this week where you can sign up. It allows you to sign up and fill out your name, the way you want it to appear on your certificate, as well as the link. You paste your Colab link for it to be there. Then you submit. So it's very simple. We'll try and get it out. The developer is still working on it, so we'll try and get it out later this week, hopefully. So please try and finish up your analysis. For those who haven't started, please strive as much as possible to start. So that's all. We've already gone past the closing time, so please go back to your resources, consume them, practice, read, understand, ask questions, and also get your hands dirty. So on this note, I'd like to thank Priya and Najam for the presentation, also to you all for listening to us and joining us on this journey. Yeah, so do have a wonderful evening.